that's my African bird.
Okay, so we've talked about similar triangles. We've had these a few times where we've had a triangle that one's an enlargement or a reduction of the other. So if I give you this angle and this angle are the same, and these two angles are the same, if I tell you that this side here is 12 millimeters, and this side over here is 24 millimeters, we established that enlargement factor, or the constant of proportionality between the two figures. So if I go on to tell you that this side is 20 millimeters, we can find this side. Exactly. We know the relationship between these two, the 12 millimeters becoming the 24, has to be the same as the relationship between those two. So the 20 millimeters will become x, and we can cross multiply and divide. And as you said, we get 40 millimeters. Well, with triangles, to know that one was a reduction or an enlargement, we had to know that the angles were all the same. In fact, in triangles, we only need to know that two of the angles are the same, because the third one had to be the same. With figures that are more than three sides, it's not quite as simple. I can have figures that have the same angles that are not similar. Or I can have figures that have the same sides that are not similar. For example, similar polygons. So these two figures here have the exact same sides. But yet, obviously, they're not equal, they're not the same, and they're not even similar, because there's no way that one's an enlargement or the reduction of the other. When it's triangles, because it's only three sides, they have no choice but to be the same if they have the same sides. So when we're dealing with polygons, we have to have not only the same sides, but we have to have the same angles. There's more than 6 pieces to work with. In triangles, a lot of times in triangles, all we need is 3 out of those 6 pieces. In a triangle, we have 3 sides and 3 angles. If I know all 3 sides, I can construct a triangle that's identical to that. If I take and I draw 3 sides that are equal to that, that triangle has no choice but to be identical to the one we started with. Even if I don't put the sides in the same order. It's just a mirror image of the original triangle. So it's still considered to be equal to that triangle, even though it's flipped over. As we've seen, however, if we have all 3 angles of the triangle the same, if those angles are equal and those angles are equal and then this final one is equal, the triangles do not have to be the same because they can be enlarged or reduced. That's our similar triangles. So it's not enough to know that all 3 angles are the same. So to know that 2 triangles are equivalent, or what we call congruent, congruent just means that all corresponding parts are equal, not just pieces. To know that those 2 triangles are congruent, we have to know at least one side is the same. So the question is how do we arrange that? So if I have 2 sides and the angle in between them, is that going to be good enough to construct a triangle that is equivalent to that? So I have those 2 sides and the angle in between them. Is there any way to construct that third side to make this triangle different? No. So if I have a side, I have the angle in between them, and I have another side, I know that those two triangles are equivalent. We saw that if we had all three sides, we were good. What if we have two sides and an angle? Or we had two sides and an angle. What if we only have one side and two angles, I should say? What if I know this side is what that side is and what these two angles are? Well, technically, if I know two of the angles, I know all three, right? Yep. So, well, but I mean, I have all three sides and an angle. So, yes, this works out. If I have that side there, and I have these two angles, no matter how I draw those other sides in, they're going to intersect at the same spot. So, yes, having two angles in one side must be, the two triangles must be equivalent. No matter which two angles it is. Here, I had the side that was between the two angles. We refer to that as angle, side, angle, for the angles in between them. If I had the side and then the angle opposite it, like this one here and one of the others, well, again, just like before, if I know two of the angles, I know all three. So this must be enough to draw an equivalent triangle. So yes, there is no way to construct that third triangle if I have that side and those other two angles. The one that we have to be careful of is when I have two sides and an angle that is not in between them. You know, the other one where we had two sides and one angle, the angle was in between the two sides. If we have two sides and an angle that is not in between them. So let's say we've got this angle and we've got those two sides. Is it possible to construct a triangle that has those characteristics that's different? Well, at first look, it's easy to say, no way to construct a different triangle. But what if instead of drawing this third side like that, I drew it like this? Do I still have the same angle here? Yep. Do I still have the same side here? Yep. So I still have the same side here. Yeah, I do. I still have those same two sides and that angle, but I do not have the same triangle. When I have two sides and the angle that's not in between them, it's possible to draw two different triangles with that information sometimes. Not all the time. What conditions have to exist to be able to draw two triangles? Well, let me show you. So in this case, if I know this angle and those two sides, can I draw two triangles? Or just one? Why can I only draw one triangle out of that? Because the side here that is opposite my angle is longer than this side. The only way I can draw a second triangle is if I can take this side and tuck it under, like I did here. For that to happen, this opposite side, the side that is opposite the angle, has to be shorter than the second side given. Normally when we talk about our triangles, we're going to name the angles. We'll call them, we'll call them sides A, B, and C for now. There it is. We name the angles with capital letters, and we'll name their opposite sides with the same letter, just a small letter. So this side here would be what side? That would be little a, because it's opposite angle big A. This side would be little b, and this would be C. The reason why we name this side for this angle over here is because that's the side that's related to that angle. If these two sides stay the same, as this angle gets bigger or smaller, this side gets bigger or smaller. So the size of side A depends on the size of angle A. And when we get into our trig, we're going to see that relationship between those sides and the opposite angles. Okay, we've already talked about a triangle. If I know two angles of a triangle, I know the third angle. If I tell you that this here is 96 degrees, and this angle here is 38 degrees, what does this angle have to be? How do we find that? Perfect. We subtract those angles from 180 degrees. So 180 minus 96 is 84, minus 34 is 46. So this angle has to be 46 degrees. Does that make sense? If I have a figure that's more than three sides, more than three angles, we mentioned that the way we find the angle sum, the interior angle sum, there's two different ways we can do it. One, 180 times the number of angles minus 360. That's that example I showed you with the triangle where we make the turns to go around the outside. Or equivalent to that is just 180 minus n minus, or 180 times n minus 2. So this is a little bit quicker form. So now here, how many angles do I have? 4 angles, so n equals 4. So this is going to be 180 times what? 2. 4 minus 2 is 2. So 360 degrees would be my angle sum there. So if I tell you that this angle here is 90 degrees, I tell you this angle is 111 degrees, and that this angle here is 90 degrees, what's this angle up here have to be? It has to be 69 degrees. How do we get that? Well, 360 is the total for a four-sided figure. Subtract 90, subtract 111, subtract 90, you get 69 degrees. So if we're looking at something like this, I tell you that's 118 degrees, 29 degrees. This one here, we're going to put it 58 degrees, 21, that's 29 there, brother. Find this angle here in your notes. See if you can find that. Nope, nothing's parallel. The first thing you got to find is the interior angle sum. How many angles are there here? 5. So n equals 5, which means we're going to do 180 times 3, right? 5 minus 2 is 3. So it's got to be 540 degrees to get around this. So then from that 540, we're going to subtract 29, 118, 58, and 21. And what do we have there? 314 degrees. So that angle is 314 degrees. which makes sense because it's more than 3/4 of a turn, and 3/4 turn would be 270. Okay, so let's look at some special cases in these polygons. Our polygons, a triangle is a form of a polygon. A polygon is just any figure with straight sides. So we had, of course, 3 sides was a triangle. We've looked at those before. Figures with 4 sides, we've looked at several of them. Does anybody know the generic term for a figure with 4 sides? A trapezoid is a special 4-sided figure. Quadrilateral. Now within quadrilaterals there are special figures. There's the trapezoid. Does anybody know what's special about trapezoid? It has 1 set of parallel sides, or 2 of the sides are parallel.
Now what are we doing?
We're just naming off special types of polygons yet. There's a parallelogram.
I gave you all these last week.
Did you?
Yeah.
So a parallelogram, of course, has 1 set of opposite, or both sets of opposite sides are parallel. A rectangle is a special parallelogram. It's a parallelogram that has at least one right angle. Of course, if it has one right angle, they're all right angles. Now, in a parallelogram, the opposite sides are parallel, which means by consequences, the opposite sides are also equal. So the same with a rectangle. Before I get to the square, I want to talk about a rhombus. A rhombus is a parallelogram that has all 4 sides equal. The reason I wanted to put that in there before I talk about a square is a square can be defined of 1 of 2 ways. A square can be defined as a rectangle with all 4 sides equal, or it can be defined as a rhombus with a right angle. Either way. So when you're looking at these, some of these can be several things. For example, a rhombus is a rhombus, but it is also a parallelogram. It's a parallelogram with all 4 sides equal. A rectangle is a rectangle, but again, it's also a parallelogram because it's a parallelogram with right angles. A square is a rhombus and a rectangle and a parallelogram. So now if we go up to 5 sides, what's a 5-sided figure called? Pentagon. Six-sided figure? Hexagon. 7? Heptagon. 8-sided is octagon. From there, 9-sided is nonagon. 10 is decagon. 11 is undeca. 12 is dodeca. We're not writing those down because above octagon they don't occur that much. So it's something you need to memorize. Generally, you can just say n-sided polygon. So rather than saying a nonagon for 9 sides, I would just say it's a 9-sided polygon is all it is. And for our purposes here, I'll get up in just a second. I'll move up. Hexagon and octagon are going to be the ones that are the most common outside of your standard square. Because if you're looking at steel stock, you can get hexagonal and octagonal steel stock. And there'll be uses for those. How far up did you need, Josh?
That's good.
That's good? Okay.
you get to like 20 and 30 sided.
Again, 20-sided polygon.
What's 7 again? 7's that?
Hepta.
Hepta?
Yep.
Where did they get that from?
You know, I'm not totally sure where the hepta comes from. Still more? Is that far enough?
We haven't given these.
You'll have a packet that should have all of it. Realistically, the odd-sided polygons, once you get above, a pentagon occurs occasionally, but really the odd-sided polygons, once you get above a triangle, just don't occur very often. So you're dealing mostly with even-sided. Did you get what you needed, or did you? Okay. So now we're going to focus in on some of the things with our triangles that are going to be useful as we get into the trig. What type of a triangle is this called?
That is a.
It's acute, but it's also isosceles. Very good. Now when we're looking at an isosceles triangle, what do we know about the angles? We know it's isosceles because two sides are equal and the third one's different. But what do we know about the angles? Two angles are the same. These two angles that are opposite the equal sides have to be the same. Because we know that in a triangle, in any triangle, the smallest side is opposite the smallest angle. And the largest side is opposite the largest angle. Here, since these two sides are exactly the same, their opposite angles have to be the same, because if one was bigger than the other, the opposite side would have to be bigger or smaller. Because of that, there's a lot of things about an isosceles triangle that are unique, that allow us to divide it up. Oops, sure. Okay. Okay. So if I have an isosceles triangle like this, and I create what's called a altitude. I'm going to say from the odd side. The odd side means the side that's not equal. Just remember what an altitude is? Okay, an altitude of a triangle. If I'm going to do an altitude from this side right here, the altitude is perpendicular from that side to the opposite angle. So it looks like that. That's an altitude. So if I draw an altitude from this side, that's my odd side, my odd length side, to that opposite angle. What do I know about that altitude? Well, what do I know about what it does to the triangle, I should say? Well, I drew it in purposely off center like that. But we know that this angle and this angle have to be the same, right? Well, we know that this angle and this angle are both going to be right angles. Correct? So those two angles have to be the same because the angles of a triangle add up to 180. So since we know two of the angles are the same, the third one must be the same. So when we draw an altitude from the odd side to that other vertex, what we create is an angle bisector. So by angle bisector, I mean it cuts that angle in half. The other thing we do down here if all three angles are the same, all we need to know is one side to know that those triangles. Is that? Oh, I was just pointing at that side of the triangle is all. So yeah, that dot doesn't really mean anything. So anyway, we know that one side is equal and all three angles are. So what that tells us is that this piece and this piece must be the same. In other words, it splits this side of the triangle in half. And that is what we call a median. It goes from an angle to the opposite side and it cuts that opposite side in half. So basically what we're saying is when we draw any of those three things, here I drew the altitude and it created the angle bisector and the median. But if I drew the angle bisector, of course, it would also have to be an altitude and a median as well. So if I draw any of those three things, an altitude, an angle bisector, or a median, on an isosceles triangle to that odd length side, it becomes all three of them. It is all three of them. And that's going to be very important for us in the trig, because for you guys, a lot of isosceles triangles come up in machining, mainly when we deal with circles. Anything that deals with items from the center of the circle and on the edge of the circle will form an isosceles triangle. So if I have 2 points here on the edge of the circle, that forms an isosceles triangle with the center of my circle, because these are just the radii of the circle. The radius is always equal to itself. What's that? Yeah, we're going to be dealing with chords. Or if you have a round piece sitting in a V block, same type of thing. Because of the way this is set, because those form right angles, this and this are equal. This side and this side are also going to have to be equal to each other. We have that same effect that cuts in half. This angle and this angle will be the same. So because of that, we're able to apply our right triangle trig. Basically what we're saying is with these isosceles triangles, we can cut them in half and we can create right triangles. It allows us to apply our trig to them. Most of what we went over today is not a lot of calculation. It's mostly vocabulary and just applying pieces. Not a lot of this is really new to you. It's just putting it together and seeing it all together. So the homework shouldn't be really hard. It's going to be out of a packet. Page 295, 1 through 24. Let me double check, see if I got to give you a new packet or if it's in the one I gave you last Thursday. Should be in the one I gave you last Thursday, so you guys should already have it. So page 295, 1 through 24 out of that packet. Again, it's mostly just identifying what pieces have to be equal and recalling names and vocabulary.